Hello everyone. Namaste. Good morning, good afternoon, and good evening. I hope you are doing all great. Well, it's late evening here in Nepal, and we are here back again with brand new episode of this webinar on Geo-Science for Sustainable Development. This is Suraj Gautam, a civil engineer and disaster risk reduction and management professional from Institute of Himalayan Risk Reduction. First of all, I would like to welcome you all in our Himalayan webinar series. Well, Institute of Himalayan Risk Reduction is an organization established with a vision to prepare a risk-informed societies for disaster resilience and sustainable development. So, to contribute onto this, IHRR has been organizing Himalayan webinar series on geoscience for sustainable development and disaster risk reduction and management. So far, we have successfully organized 5 episodes of webinar on geoscience for sustainable development. And yes, it's the turn for the 6th one. And today we'll be having an interesting topic on the architecture of the metamorphic core of the Himalaya, which will be presented by Professor Dr. Rodolfo Carosi. On behalf of the organizing team, we are really grateful to our presenter who will be sharing us with his healthy insights and experiences. So it is indeed an honor to welcome our presenter, Professor Dr. Rodolfo Carosi, who is a professor at Department of Earth Science, University of
Hey,
Torino,
hello.
Italy. Hello, sir. Namaste. So, to make this session more
Hello, namaste, namaskar.
to make this session more interactive and lively, we have Assistant Professor Dr. Basanta Adhikari from Institute of Engineering, Tribhuvan University, as our session moderator. And Dr. Adhikari is also the visiting scientist at Institute of Himalayan Risk Reduction. We'd also like to welcome all of our participants and regular attendees who are joining us through our social media live streaming and also through the Zoom platform. This webinar event has also been featured in the website of Relief Wave, which is under OCHA services and is the largest humanitarian information portal in the world. Talking about the webinar registration, till date, we have about 198 registrations from different parts of the globe. So to address this request, we are going live as usual on our social media page of Institute of Himalayan Risk Reduction. And we'll also be receiving the queries and feedbacks from our social media live streaming and as well as from our Zoom chat box. So we have been organizing this webinar series on geoscience for sustainable development on a regular basis. We believe this webinar series has been supporting our early career scientists, DRR professionals, academicians, and all the participants. And yes, it is just the beginning and we'll have a long way ahead. So before starting our session for today, I'd like to give a very brief introduction about Institute of Himalayan Risk Reduction. IHRR is an organization established with an objective to assess and understand the risks to contribute for the sustainability. IHRR works under the 4 thematic areas, that is disaster risk reduction and management consulting, research and development, disaster academy, youth in DRR, and management. Our team consists of professionals with expertise and experiences in the field of disaster risk reduction and management in understanding the risks, conducting academic research and field level implementations in Nepal and across the globe. So far, we have successfully accomplished a number of projects, which includes our collaborative approach during this COVID-19 response. We collaborated with the number of stakeholders and then contributed for the development of national portal for the information dissemination during this COVID-19. And it was also endorsed by the Ministry of Health and Population of Government of Nepal. Besides, during this lockdown period, utilizing this period, we also had a UAV surveying of Hetauda sub-metropolitan city. So far, we have already captured more than 110 square kilometer area. So we are also working on its processing. And besides this, we have also published a voluntary commitment on the Sendai voluntary commitment platform, and it has also been featured over there. And this is what we have been doing during this period, Himalayan webinar series, which we have been conducting under 2 themes. And today, here we are having our webinar topic on the architecture of the core of the Himalaya. So Now I would like to share some house rules for today's webinar. The audio and video of the participants will be switched off. The overall session of the webinar will be recorded. For any queries, the participants can write up in the chat box or in the comment section of the Facebook streaming live. And the waiting rooms has been enabled, and only the registered users with their original identity will be allowed to enter the webinar room. And also, I would like to request our participants to please rename and keep their name as mentioned in the registered link. I would like to request all of our participants to strictly avoid using the annotations. Annotating during the presentation will be taken offensive and the participant will be removed from the webinar. So feedback links will be provided during the session, and we'll be providing the participation certificate as well. Well, to add upon this participation certificate, we have almost prepared the participation certificates of our previous webinar as well. So we'll be issuing it as early as possible. So without any delay, I would like to now move on to our session, and may I request Dr. Basanta Adhikari to proceed further with his moderation. Thank you for now.
Thank you, Suraj. Am I audible now?
Yes, sir, you are audible.
Yeah. Thank you, Suraj, for your introduction about Institute of Himalayan Risk Reduction and the concept and then the procedure of the webinar. Yes, it's always a pleasure to invite all our distinguished guests who are working in the field of geoscience and then to share their experiences. And today we have requested Prof.Dr. Rodolfo Carosi, who is a professor of Department of Earth Science, University of Torino, Italy. And I met him a couple of years before, and when he was working with his students and colleagues in the Nepal Himalaya. And then I have been following him, and then we met in a couple of conferences and seminars, and we are very happy to read his insight about this Himalayan evolution of Himalayan origin, and especially I'm always interested to read his some kind of reports or research papers in Kaligandaki, as I'm working also there. So Professor Carosi graduated at Pisa University and a full professor at the University of Torino since 2011. He is specialized in structural geology and tectonics with a special focus on evolution of modern and ancient orogenic belt spanning from Himalaya, Antarctica, Alps, southern China, Albania, Spain to Sardinia and Northern Apennines, so mostly covering all around the globe. His aim of the researches includes understanding the growth and collapse of orogen, continental transpression tectonics, deformation, metamorphism, and exhumation of deep-seated rocks, strain and kinematics of high-strain shear zone. His expertise lies in the tectonics, regional geology, which mostly focus on geological mapping and synthesis and structural analysis, including microstructures, outcrop, and regional scale. Structural analysis is performed also by the microstructural investigation, relations between deformation and metamorphism, and then finite strain and vorticity of the flow. Recently, quantitative-oriented studies includes numerical simulation of high-strain shear zone and a mathematical approach on deformation are his interest. So he's mainly, he's mainly interested in the field-oriented studies dealing with the ductile and brittle deformation processes, evolution of crustal scale shear zones and faults, and associated microstructural fabric development and fault-fault relationship, geological field mapping. Moreover, he's also interested by the application of uranium-thorium-lead geochronology and argon-argon thermochronology to continental tectonics. Currently, he's working with the structural evolution of the Great Himalayan Sequence and Tethyan Sedimentary Sequence in the Central Himalaya, with emphasis on the models and timing of exhumation of crystalline unit. He's also involved in a project focusing on the tectonic evolution of Rosa orogen, Antarctica, and tectonic units in the Alps and Northern Apennines. So he has already published more than 100 papers in international peer-reviewed journals, and yes, geological maps. He's quite well known in Italy, also in Nepal, India, Himalayas, and around the globe in the field of tectonics. And we are very pleased to invite him to give a talk on the architecture of the metamorphic core of the Himalaya. So Professor Carosi, the virtual room is yours. Please proceed.
Okay, namaste. First of all, I would like to thank you, Surai Gautam and Basanta Adhikari, for inviting me to this talk. I now try to share the presentation. Do you see the presentation now?
Yes, yes.
Oh, okay. Okay, the topic is the architecture of the metamorphic core of the Himalaya. Oops. Okay, as you know very well, because you live here, the Himalayan belt is the most classical example of a continental collision after the collision between India and Eurasia. In this picture, we can go to give a much more close look to the Himalayan belt. With color, I indicated the tectonic units derived from the northern Indian continental margin, just to the south of the suture, of the Indus suture, the red line here. With the yellow color, I indicated the Tethyan sediments, whereas with violet, I indicated the greater Himalayan sequence, and with green, the lesser Himalayan sequence. The metamorphic core of the belt, as you know, is made by the greater Himalayan sequence, the violet color, where metamorphic rocks and Miocene leucogranite crop out. Okay, in this block diagram, we can see the higher Himalaya or greater Himalayan sequence, that is the main metamorphic unit, that is bounded to the north by the famous South Tibetan detachment, a system of low angle normal fault and shear zone, with top to the north and down to the north and northeast sense of shear, with a displacement reaching at least 200 kilometers. We can see here a leucogranite of Miocene age deformed by SC structure, indicating a top to the north sense of shear. To the south, the greater Himalayan sequence is separated by the lesser Himalaya, as you know very well, by the main central thrust zone, a huge zone of deformation, separating the greater Himalayan sequence from the lower lesser Himalaya. The sense of shear is top to the southwest. Sorry, there is a problem with the timing.
You can.
Okay, here we can see a picture of the South Tibetan detachment taken from Rombuk Valley in southern Tibet, cutting across the top of the Mount Everest. Here we can see the cataclysite characterizing the South Tibetan detachment system at the altitude of 8,500 meters. And in this picture from Legeson and others, 2015, we can see the trace of the South Tibetan detachment deep into the north, and we can encounter or meet the South Tibetan detachment in the Rombuk Valley. We can see here a beautiful, there is just a road at the altitude of 4,000 meters. We can see fossils and the sediments of the Tibetan sedimentary sequence in the upper part. Here we can see Brachiopod over the Vishan ages, just put above the metamorphic rocks of the greater Himalayan sequence. So we can see here sillimanite and biotite bearing gneiss, as well as the whitish stuff is made by leucogranites deformed by the South Tibetan detachment. Also at the micro scale, we can see beautiful kinematic indicators such as mica fish and the dynamic reclassification of quartz, indicating a top to the north sense of shear. So this Tibetan sedimentary sequence is shifted down to the north for more than 200 kilometers by the South Tibetan detachment system. Here we can give a close look to the South Tibetan detachment with a breccia made by Ordovician limestone on the left, just above the gray stuff made by sillimanite and biotite schist, as well as leucogranis, the whitish stuff. If we go down at the bottom of the Greater Himalayan sequence, we can see in Garhwal, India, the main central thrust with the Greater Himalayan sequence on the left here, and the Lesser Himalaya on the right, with intervening beautiful myelonites, such as the picture below, with S-C structure and mica fish or foliation fish, clearly indicating a top to the southwest sense of movement. But up to now, the Greater Himalayan sequence has been regarded as a coherent tectonic unit bounded by these two main shear zones, the main central thrust and the South Tibetan detachment. But is it true? Because usually some thrust or shear zone have been detected in the metamorphic rocks, but they were usually interpreted as out of sequence thrust with respect to the main central thrust. It is a thrust younger than the main central thrust. So we asked, are they all really out of sequence thrust? What about the age, the kinematics, the PT condition during shearing? It's a problem. And for example, we can observe in the Kalingadhari Valley, a beautiful section across the Himalayan belt, the Kalopani shear zone in between the main central thrust, the blue line, and the South Tibetan detachment, the red line. The Kalopani shear zone dated at 12-15 million years by Van Den and Ogis in the 90s. And this is a classical, regarded as being a classical out of sequence thrust, such as other thrust in Bhutan, the Kaktan thrust, the Zimitan thrust, or other shear zone, the Modikola shear zone, and other shear zone in Eastern Nepal. So every thrust or shear zone is usually regarded as younger than the main central thrust. Now we give a look to the rocks and moreover to the deformation inside the metamorphic core. In the Greater Himalayan sequence, there are a lot of migmatites, especially in the higher part, with leucosome intruded in shear zone or in axial plane of faults. On the right, you can see migmatite with folded leucosome. And in the picture to the bottom, we can see some other feature of the Greater Himalayan sequence, the huge occurrence of myelonites. For example, in the picture, the bottom left, we can see a myelonite from the Mugu Karnali. The thickness of this myelonite is 4 kilometers. And in the bottom right, we can see a shear plane with a growth of sillimanite at the centimeter scale in the Marshandi Valley. Okay, the upper part of the Greater Himalayan sequence is intruded on the bottom right, the migmatite of the Greater Himalayan sequence with a lot of leucosome grouping and reaching the Makalu granite. Okay, in the last 20 years, we investigate several sections of the Greater Himalayan sequence, spanning from Western Nepal, Central Nepal, Eastern Nepal, as well Bhutan and Sikkim. And now we are moving in the northwestern part of Himalaya, in Garhwal, Uttarakhand. And we try to investigate the shear zone and the thrust using a multidisciplinary approach. This approach has been suggested by Montomoli and others in 2013 in a paper published on tectonophysics, and we tried to join structural geology at a mesoscopic scale, at the micro scale, with petrology, aided by the use of isochemical pseudosection, as well as geochronology, or better, petrochronology. That is the use of geochronology aided aided by the use of chemical map of the minerals that we are trying to date. In this picture, we can see a monazite with a chemical zonation in yttrium. So if we join all this information, we can gain a lot of useful information to better understand the shear zone, the meaning, the age, the PT path. So I will show you now the last example of the shear zone studied in central Nepal, in the Marsiandi Valley, in between the Manaslu and the Annapurna Massif. And we try to identify what we call tectonic and metamorphic discontinuity, or higher Himalayan discontinuity, as named by Montomoli and the others 2013 and 2015. That is a shear zone, a huge shear zone within the greater Himalayan sequence above the main central thrust. We usually go in the field and we try to build up geological maps to collect structural data, foliation, lineation, kinematic indicators. We usually collect a lot of sample, maybe 100, 150, 200 sample. We analyze the sample in the lab for microstructure, petrology, geochronology. We try to obtain good data. We try to better interpret this data. At the end, we can try a tectonic interpretation of all this stuff. Okay, in this map, you can see the Marsiandi Valley. In yellow, with the yellow color, is indicated the main central thrust zone near Kudi or Bulbule. There is a lower main central thrust. Boundanda, there is an upper main central thrust. The South Tibetan detachment is here in the upper part, in between Chami and Bratang. And in between, just north of the village named Jagat, we found a shear zone, a ductile shear zone. You can see here the sense of shear that is top to the southwest. The shear planes deep to the northeast, as well as stretching lineation plunge to the northeast. So that it is a contractional shear zone just to the north of Jagat. In this sample that I showed you before, you can see silimanite growing along the shear planes, where kyanite is a relic mineral affected by deformation. Okay, in this cross-section, we can see the position of some sample. We collected more than 100 samples, but we selected 4 samples for geochronology or petrochronology. One just along the Myelonitic shear zone that we named HHD, one in the upper greater Himalayan sequence, and 2 samples in the main central thrust zone. There are usually myelonitic gneiss, migmatitic gneiss, and so on. Typical rocks of the greater Himalayan sequence. In this picture, I show you a scene section where the position of some monazite, that is it is a mineral useful for gain datation of the shear zone. We analyzed the monazite by electron microprobe. With EMPA, we detected the chemical zonation of the monazite. This is a very important step because when you gain several datings in one single crystal, it is difficult to put the ages, in relation to prograde or retrograde metamorphism or to shearing. But if we join the chemical zoning of yttrium, it is more easy to interpret the age. Come back. Okay. And here there is a monazite after laser ablation. Laser ablation was made by John Cottle in Santa Barbara, California. It's a very nice instrument. I will show you here why monazite is so useful. It's a small mineral, but it's very important because when you have mica schist or gneiss with garnet and monazite, they grow together, and during prograde metamorphism, all yttrium and rare earth elements are sequestrated by garnet. So the contemporaneous monazite is depleted in monazite during prograde path of the metamorphic rocks. During the retrograde path of metamorphic rocks, we can observe a breakdown of garnet or resorption, and yttrium and rare earth element are released, and they are sequestrated by the contemporaneous monazite. So the monazite starts to show a high yttrium rim. So when we have this situation, we can well interpret the ages in different position in the same grain. Okay, I can show here two examples of two samples. The sample along the HHD, the Jagat shear zone in the Marciandi Valley, and the one sample in the upper GHS, just to show you the process. We can see here in this picture a clear zonation of yttrium, and the core is depleted in yttrium. There is a very low amount of yttrium. So these ages could be related to the prograde path of the monazite and the rocks. The high yttrium rim is represented here by yellow and red color, show the younger ages, and these ages are related to the retrograde path of a rock when garnet is destabilized and release yttrium and rare earth element in the rocks, and they are sequestrated by yttrium. The opposite happen for thorium. The thorium and yttrium show an opposite zoning, mineral zoning, chemical zoning. So in these two graphs on the left, we can see in red all the prograde ages, because in each sample we detected maybe 10, 11 monazite, and for each monazite we analyzed maybe 10 points with 10 ages. So we can put all the ages in this graph, and with the red line we indicated the prograde ages in red, and with green color we represent the retrograde ages. So the boundary from prograde and retrograde is 25 million years for the shear zone, and the 27, 28 million years for the upper great Himalayan sequence, a sample just above the shear zone. They give more or less the same indication. So if we put analyze the sample together, we have a first group of ages from 38 to 25 million years are interpreted as prograde metamorphism, and the 27, 25 million years up to 15, the retrograde metamorphism. Okay, we can use also some other indicators. For example, together with the yttrium versus ages, we can use also the ratio gadolinium-ytterbium that show a decrease of the ratio towards younger ages. This is a confirmation of the data that I showed you before. So there are several possibilities to constrain the prograde and retrograde ages. It is interesting to compare the ages in the hanging wall of the shear zone, in the upper part of the shear zone, with the ages found in the footwall of the shear zone. In this graph, you can see hanging wall and footwall. We used also a nice sample in the lower part of the Great Himalayan sequence from Gibson and others, 2016. And we can observe this particular situation. In the hanging wall, the shift, the transition from prograde metamorphism, the blue color, with the retrograde metamorphism, the yellow color, can be put at 26, 27 million years. If we give a look to the footwall, the same transition between prograde and retrograde metamorphism happened 10 million years later at nearly 17 million years. So there is a shift of the transition from prograde and retrograde age metamorphism in between the hanging wall and the footwall. The shift is nearly 10 million years. How we can explain this different situation? in the upper part of this slide, we can see a cumulative age of the hanging wall of the shear zone, not only in the Marciani Valley, but also in other positions in the Greater Himalayan sequence. And this is a very common feature. The hanging wall show this transition at 25, 27 million years, and the footwall more or less 9, 10 million years later. Why this happens? We must remember that we are dating a sample just above the shear zone that is represented by the red thick line in the figure below, with a contractional kinematics top to the southwest. We must remember the kinematics of the shear zone. We can see in green the future South Tibetan detachment system above, and below the future main central thrust. At 28, 27 million years, the HHD, or Jagat shear zone, or mid-Himalayan discontinuity, started to be active. What happens to the samples in the hanging wall? If we give a look to the sample named A1 in the hanging wall, he moved to position A2 because the shear zone has a contractional kinematic. So the points are displaced towards the south. And this is confirmed by the PT path on the bottom right. You can see point A, decreasing pressure and temperature for the activity of the shear zone. But what happens in the footwall? The footwall, if we can see the arrow here, continues to move downward, and the point B1 is shifted to position B2, increasing pressure and temperature. The same point is represented in the graph to the left, and the B1, increasing pressure and temperature, moved to position B2. So the different path, metamorphic path of the hanging wall and the footwall is due to the activity of the shear zone that started to be active at 28 to 27 million years up to 70 million years. So the shearing continued for 10 million years, moving the hanging wall upward and the footwall downward. This causes a difference in the PT history of the rocks above and below. So the tectonic metamorphic discontinuity that we found in the Marciani Valley is a shear zone lasting at least 10 million years. The geometry and the kinematics of the shear zone, top to the south and southwest contractional, affect the metamorphic paths of the rocks in the hanging wall and the footwall. Petrochronology, which is the use of chronology with chemical zoning of the dated points in the monazite, allows to detect and to date the PT path of the rocks of the hanging wall and the footwall, highlighting the diachronicity of the maximum PT conditions. There is a shift of the PT condition due to the kinematics of the shear zone. Without the shear zone, the situation has no difference, but with the activity of the shear zone, we can observe this difference in the PT paths of the rocks. So the maximum PT condition have different ages in the hanging wall and in the footwall due to the activity of this huge, ductile, high temperature shear zone. Oops. Okay. At this point, the question is, this shear zone, Jagat shear zone, tectonic metamorphic discontinuity, or high German discontinuity, is a local or is it a regional feature? To do this, to answer this question, we made a lot of field work, and we made maybe 15 expeditions in the higher Himalaya, starting from Western Nepal. You can see a schematic geological map published in 2018 on Earth Science Review, where we put the Tibetan Himalayan sequence in brown, the Greater Himalayan sequence in blue and violet, with the shear zone, the HHD, inside, dividing the greater Himalayan sequence upper from the greater Himalayan sequence lower. And we can trace this shear zone for at least 100 kilometers from Mugu Karnali here, Rara Lake is just here, to Tarakot, just to the south of Dunai in this part. In green, you can see the less Himalayan sequence and the main central thrust zone for main or lesser Himalayan crystalline as named by Fuchs several years ago in yellow. Okay, we detected the shear zone firstly here, and we continued to in several other sections. For example, here we can see a small geological map of the Kaligandaki. You can see at the bottom the famous main central thrust outcrop close to Dana, a very famous position of the main central thrust after the fort 1975. And we can see here the position of the HHD just here, north of Dana, that we named the Chomrong Thrust. And we can follow the Kaligandaki, and in the upper part we can see the South Tibetan detachment. And here the Kalopani shear zone, and we come back to the Kalopani shear zone in a few minutes. Okay, all this shear zone in Western Nepal, Central Nepal show the very similar characteristics. They show beautiful myelonites with top to the south and southwest sense of shear planes deep to the northeast, stretching lineation plunge to the northeast. We can see also some rotated porphyroclast or some SC prime structure. At the micro scale, we can observe the growth of a sillimanite along a shear plane. The formation mechanism of quartz, so we can observe grain boundary migration or chessboard extinction in quartz, indicating temperature higher than 600 degrees. So very, very similar feature in all the section that we studied and we observed. We also detected the PT path of the rocks in the shear zone, in the hanging with the footwall. I have no time to go into detail of this complicated topic, but in this picture, published in 2019, we put the PT path of the shear zone in the same PT space, but it is worth to note that the myelonitic foliation developed mainly during decreasing PT condition, when the rocks start to be exhumed, diminishing pressure and temperature. This is true for Western Nepal, Central Nepal, for all the shear zone that we detected. The myelonitic foliation developed in these decreasing temperature and pressure conditions. We also use the same methodology, uranium, lead, thorium analysis by laser ablation for the Mangri shear zone, for the Tojem shear zone, Chomrong Thrust, Jagat shear zone, and we obtained very similar ages, 25 to 17, 26 to 17, 25 to 18, 28 to 15 million years. So this shear zone has been well constrained in ages in all the sections that we studied using the petrochronology and chemical zoning of monazite. It is very important to note that the HHD, our ductile shear zone, is always older than the main central thrust along the same section. We used in this paper 2015 our sample and published data from other people such as Larsson, Corin-Cohn, Larsson and Kottol, and always we observed older ages of the HHD and an upper structure position. Okay, about if we go down, we have the main central thrust, and the main central thrust is usually younger, as we can see in this column on the right. You can see ages spanning from 22, 13 million years, 21, sometimes 9 million years. In a recent paper by Montemagni and the Igor Villa group of Milano Bicocca in Italy, in 2 papers, the staff of people dated the upper main central thrust and the lower main central thrust in Garhwal and the Uttarakhand, famous Vaikrita and Munsiari thrust in northwest India. And it's very interesting because the Vaikrita thrust was constrained at more or less in this position at 9 million years in Alaknanda, Dauliganga valleys and 8 million years, 7 million years in the Bhagirati Gangotri. Whereas the Munsiari thrust was younger with ages spanning from 5 to 4 million years. So very, very young ages and much younger with respect to the HHD. Okay, analyzing the section directly in the field, collecting sample, or analyzing the paper published by colleagues, we were able to trace this shear zone in the middle part of the Greater Himalayan sequence for more than 1,000 kilometers from western Nepal, Mugukarnali, up to Sikkim, you can see Gangtok, and Bhutan, where the Kaptan thrust, usually interpreted as out of sequence thrust, was older, with ages 27, 19 million years. So we can trace this tectonic feature for at least 1,000 kilometers. And now we are working the Greater Himalayan sequence in northwest India, and we detected the same shear zone, and we are preparing the paper with the help of PhD students in Turin. And we'll publish in the next month, I hope, the results. So we can extend the occurrence of the shear zone further to the northwest. Okay, so this shear zone, we can obviously divide the Greater Himalayan sequence in 2 portions, an upper portion and the lower portion divided by the HHD, active between 27, 28 million years up to 17, 16 million years. Some out of sequence thrusts still exist. They were detected by Ambrose Larson in eastern Nepal, with ages younger than 20 and 18 million years. It is very, very important also for the exhumation of the metamorphic rocks, because the kinematics of this shear zone caused the exhumation of the GHS upper. The upper part was exhumed starting from 27, 28 million years. And we called the mechanism for exhumation by the activation of shear zone, younger shear zone to the south, and in sequence shearing mechanism that we published on Geological Society of American Bulletin in 2016. Because we can observe younger ages toward the south and the bottom of the Greater Himalayan sequence and main central thrust. Okay, in this picture we can see what I described by words. From collision onwards, the Greater Himalayan sequence underwent a progradient metamorphism with increasing pressure and temperature. At the time of activation of the HHD of the shear zone, the upper part of the Greater Himalayan sequence became exhumed. The point stopped to move downward and started to move upward. Then there went exhumation. Due to the kinematics, you can see the black arrow of the indicating the kinematics of the shear zone. So the upper part started to be exhumed. After 10 million years, at 17, 16 million years, main central thrust was activated, and all the Greater Himalayan sequence, upper and lower, were exhumed as a coherent unit, but only at the time of activation of the main central thrust. Before, the Greater Himalayan sequence was divided in 2 different portions with different time of exhumation, as highlighted by the ages of monazites that reported on the right of this slide. You can see progressive metamorphism in GHS upper, and the progressive metamorphism in GHS lower is shifted for 9-10 million years for the activity of this ductile shear zone in the metamorphic core. But the game is not yet over. We come back to the Kalopani shear zone. You remember the Kalopani shear zone. I show you at the beginning as a classical example of out of sequence thrust because of argon-argon edges on white mica. It was regarded as younger than the main central thrust. We mapped the Kalopani shear zone by a PhD student, Lorenzo Gemignani, now research at Germany, and he was able to trace the Kalopani shear zone from the main part of the Kaligandaki up to the Annapurna base camp, and we collected the sample from gneisses. You can see orthogneiss here with myelonitic deformation top of the southwest sense of shear, as well as the paragneiss with garnet and starolite, the sample KL19. We dated the two samples by monazite with the same methodology, and we obtained concordant ages of monazite along the main foliation, indicating the ages from 41 to 30 million years. We had also older ages in monazite inside garnet from 42 up to 48 million years. It's important to relate this, the growth of monazite with the retrograde path of the rocks. We can see the gray arrow shows the PT path of the rocks of the Kalopani shear zone. And we constrained the growth of monazite during the retrograde path. So during the formation of this foliation at top to the southwest sense of shear, in the uppermost part of the Great Himalayan sequence, we observed the first exhumation of the metamorphic core. So we need to put not only an HHD above the main central thrust, but also another shear zone in an uppermost position that we called Kalopani shear zone because it compounds close to the village of Kalopani in the Kaligandaki, and the age is 41-30 million years. The HHD show ages 27, 17, 16 million years. The main central thrust is always younger, 17, 13 million years. For this reason, we called in sequence shearing deformation, because the older shear zone are in an upper position and the younger shear zone are in a lower position. The data that we gained from the main central thrust in northwest India confirmed this picture, this framework, because the Vikrita thrust, the upper part of the main central thrust, has been constrained at 8 million years with static white micas cross-cutting the myelonitic foliation dated at 6 million years. After that, Munziari thrust, the lower part of the main central thrust zone, activated at 4-5 million years. So the in-sequence shearing started from Kalopani shear zone, higher Himalayan discontinuity, main central thrust upper, and the main central thrust lower. So at the end, when we compare some model of the exhumation of the Great Himalayan sequence, starting from the famous channel flow, or critical taper, or wedge extrusion, or wedge insertion by Webb and others, or in sequence shearing, I can say that the data that we obtained along the belt, dating the shear zone, the exhumation, the PT path, and the activity of the ductile shear zone, point to an in-sequence shearing mechanism of exhumation. It's important also to say that with these younger ages of the main central thrust, it is unlikely that the South Tibetan detachment and main central thrust was coeval all through the Himalayan belt. Maybe sometimes are coeval, but for the most part, they acted in different times. For example, we found in Western Nepal a granite, a huge granite, including the South Tibetan detachment, with an age of 25, 24 million years. So the contemporaneous activity of South Tibetan detachment and main central thrust, that is very important for the model on the left, the channel flow, the wedge extrusion, and the wedge insertion, is not confirmed by our data. So the most probable mechanism are the critical taper and or in-sequence shearing. This is just based on our new data. So we are at the end. Just to go into a few conclusions, the greater Himalayan sequence is no more a coherent mega unit, but it is affected by contractional shear zone, HHD and Kalopani, dividing it into 3 different portions. HHD was active before the main central thrust, but in an upper structure position. We have a long-lasting shearing of the HHD of this shear zone in the ductile realm for at least 10 million years. Due to this long activity, the shear zone was able to affect the PTT conditions of the rocks above and below, the hanging wall and the foot wall. The timing of activation of Kalopani, shear zone, 41, 30 million years, HHD, 28, 18, 17 million years, main central thrust, upper, Vaikrita, 9, 8, Munziali thrust, 4, 5 million years, suggests an in-sequence shearing mechanism for the exhumation of the metamorphic rocks. So this is a huge work that we that we made in the last, at least in the last 20 years, but we started before, personally in 1993. And it is not, of course, the work of one person, but it is the work of the huge group of persons. And I would like to say thank to the group work made by Chiara Montomoli, Salvatore Iaccarino, Dario Visona, first of all, my friends in maybe 20 expedition in the Himalayan belt, and all the students and PhD students involved in this lasting research. A very nice research group in the field and in the lab. So thank you very much for your attention.
Thank you, Professor Carosi, for enlightened talk. I would like to request our participant to post your questions and comment there in chat box. But in the meantime,
yes,
I would like to share my screen. So, I just take this condolence message from Nepal Geological Society, because we lost our great hero and great man, great human being, late Professor Dr. Gerard Fuchs, who had spent his time in this Himalayan region, and he was born in 1934, and he passed away in 2088. So Nepal Geological Society, as well as our geoscientists around this region and the globe, express the heartfelt condolence on sudden demise of our professor and honorary member of Nepal Geological Society, Professor Dr. Gerard Fuchs. I met him back in 2009 when I was doing my PhD in University of Vienna, and he was such a lovely man and great human being, and we miss his presence and remember his remarkable contribution in geoscience in the Himalayas, and may Almighty give enough strength to Fuchs' bereaved family to face this sad situation. And we always remember his work, and maybe Professor Carosi and Professor Hubbard and Chegira and Professor Kaviraj Paudels and others who are joining this season met him during our excursion and the conferences. And so our heartfelt condolence to this great hero. Do you want to share something, Professor Carosi, and to
yes.
Dr. Fuchs?
Yes, yes.
Okay, so now I will take questions from chat box.
Yes, I just started reading some questions.
Yeah. So first question from Upendra Baral. He's asking the mechanism of emplacement of leucogranite has any relation with the activation of STDS, and you mentioned deformation in leucogranite. So is it due to STDS? Also, some groups like Adhikari are arguing that India is a collision age as Miocene. Do you think this leucogranite is due to this younger collision? Also, Professor, could you explain some more about the exhumation of higher Himalaya?
Mm-hmm.
And there is another associated question with that also. He's mentioned that, as you mentioned, this Great Himalayan sequence upper and Great Himalayan sequence lower. So could it be possible that upper part was exhumed at first and later covered by Tethyan Himalaya, and later lower part was exhumed later during the Miocene? What's your impression on that?
Okay, very nice question. About the mechanism of emplacement of leucogranites in the South Tibetan detachment, I think that melt can cause strength softening, so can activate the localization of the formation along the South Tibetan detachment. The ages are usually 25, 24 million years, but I don't think that they are linked to the younger collision, because you need to bring the rocks at depth to melt them. The melt migrates, and you need several million years to melt these rocks, and part of this melt is due also to the compression. So you cannot realize all this stuff in just 1, 2, 3 million years if the collision is so young. We also obtained, for example, several monazite ages in garnet or starolite or kyanite, indicating ages of 48, 49, sometimes 50 million years. So this means that the rocks were already down in very old ages. So younger collision is not so well constrained for the metamorphic point of view. Okay. About the possibility to have Tethyan Himalaya rocks covering GHS upper, is it possible? But now what we can see is exposed. So what happened maybe 40 million years, I have no evidence. I tried to have evidence of the older exhumation and deposition of grains in the foreland, but there are ages not so old. The ages are the first signals of metamorphic rocks from the Great Himalayan sequence are 26, 25, 27 million years, just as the age of the HHD, not older.
Thank you, Professor Carosi, for your explanation. Yeah, it's not easy to answer this kind of theoretical question.
Very complex.
I can imagine that. And very interesting question from Mary Hubbard. So she's asking, given that thrusting does not cause exhumation, are you calling on erosion of the hanging wall for exhumation or movement of the STDs?
Okay, you're right, Mary, because only thrusting cannot cause exhumation and diminishing of pressure. So what we can observe from the rocks is that the pressure is decreasing. So we can invoke erosion, but we have not all the evidence of erosion older than 27 million years, but maybe also mechanical thinning of the Great Himalayan sequence, because there are several papers pointing to thinning of the Great Himalayan sequence due to vorticity to the combination of pure shear and simple shear, because you thin the sequence by pure shear, the pressure decrease, and this could help to exhume the greater Himalayan sequence. And also, maybe older activities of the South Tibetan detachment could help the exhumation. So you're right. We need some of the three aspects to exhume the metamorphic rocks. Excellent question.
Yeah. Yeah, that's very interesting question. I can imagine that also. And so another question from Dilli Ranthapa. It's still billion-dollar question. So what is the controversy on main central thrust, whether this is still active, or what's your view on that? Or
for what I know, main central thrust is very young, but I have not seen evidence of reactivation, of actual reactivation of the main central thrust. White mica can arrive at 4 or 5 million years. There are some monazite in Marciandi Valley by Elizabeth Catless up to 3 million years, but I have never seen evidence of reactivation, actual reactivation of the main central thrust, just on the same surface. So for me, it is not active now.
Yeah.
For what I know,
yeah.
But
yeah, evidences also show that MCT is not active now, but it's still the location of the MCT is still controversy.
Yes, yes.
Yeah, there is a long question from Karbiraj Pauril, sir, because he is also working with you and visited your institute. So, so he has lots of questions. You can look over there, but I will read it out. So excellent presentation. I have some questions to Professor Carosi. So Kalopani shear zone, why not a thrust fault, but just a shear zone 1? Similarly, what is the chronological relation of main central thrust activation and reactivation of Great Himalayan sequence and Kalopani shear zone? And the another question is, what are the evidences to say that Greater Himalayan sequence is a coherent tectonic unit with MCT and STDs, where these shear zones nicest link with collision or extension mechanism of the Himalaya? And the final question, what do you say the reason between MCT1 and MCT2 is like a shear zone like a Greater Himalayan sequence / Kalopani shear zone? So there are lots of couple of questions. So you can just look it and give try to give the answers one by one, Professor Carosi.
Yeah, very very complex question by Kabirai. Relation to activation. Okay, the evidence to say that Greater Himalayan sequence is current tectonic units at the time of activation of the main central thrust is because, for example, in the Toijem shear zone, just north of Jumla district, we found leucogranic dikes undeformed, cross-cutting the Himalayan foliation, dated at 17 million years. We published on a paper in 2010. So we have evidence of ending deformation. There is shearing, the deformation ends, cross-cutting dikes, and then activation of the main central thrust. So the shear was localized, the shearing was localized on the main central thrust and no more in the upper part. So for me, when the main central thrust started to be active, the other part was a big current unit. But only at the time of main central thrust, maybe 18, 17 million years onward. In the older ages, the Greater Himalayan sequence behaved as 2 or 3 different mega units or crustal slice. Okay, the genesis is collision of the shear zone, contractional deformation. Still India pushing with Asia, contractional tectonics cause this reverse shear zone thrust. So no true extension in the Himalayas. Maybe when you can observe extension in the South Tibetan detachment, there is no tectonic extension, but it is a fault like a stretching fault named by Means 1980. It is the upper part is stopped and the lower part move to the south, or there is a sort of compensation of the taper, because you thick the belt, you need to have a local extension to compensate the thickness. A mechanism like the Platt model for the tectonic wedge of the pavement. So there is no true tectonic extension, but the extension is a consequence of the thickness of the greater Himalayan sequence or of the movements of the fault, for me. Final question, what do you say the region between MC2 and MC2? Is the shear zone like GHS Kalopani? I don't understand very well this question, because they are different position and different ages of, and the rocks are also a little bit different. Maybe from MCT1, MCT2, there is a huge zone of myelonites, continuous myelonites, but probably with different ages of activation. You can see in the field now maybe 2 kilometers of myelonites, but this not means that all the myelonites were contemporaneously active. There is probably an activation of the upper part, of the middle part, and then a lower part. What we can see from the ages of the white micas and cross-cutting ages of cross-cutting cross-cutting muscovite with younger ages. So it is evident that the upper part of the critical thrust stopped at 6-7 million years, and then the formation shifted downward. But you preserve the myelonites in all of the section. I hope to have answered to Kabi. Maybe we continue the discussion.
Yeah, we'll continue later on. So another question from Ravi Kumar, but Dr. Boral has already explained a little bit, but he's asking South Tibetan detachment system, is it a normal fault or a thrust fault?
Okay, actually, what you can see from the kinematic indicators is top down to the north. So it is a normal sense shear zone. But probably before it was a thrust fault. When Tibetan sedimentary sequence thrusted onto greater Himalayan sequence, so for example, in the Zanskar shear zone in northwest India, Mukherjee found, a geologist from India, found previous kinematic indicators indicating a top to the south movement before the normal activation. So probably it was first a thrust and then reactivated as a normal fault and normal shear zone. But what we can see now is an evident normal movement.
Yes, I agree also on this. So another question from Nilis. So asking very enlightening presentation. So what is your opinion on the role of fluvial incision in exhumation of metamorphic cores in the Himalayas?
Of course, it plays a very important role in the last part of the exhumation, because you need to bring the rocks on the surface, and then you need to build up a relief. Then you can start to build up a fluvial incision. So in the last part of exhumation, they help to move the rock upward, of course, because a lot of erosion by monsoon activity. So it helps a lot to exhume in the last part of the history.
Yes, thank you, Professor. So another question from Facebook, I am taking, so from Baburaj Genwali. So his question also a little bit with Dr. Paudel. Is the Kalopani shear zone continuous like the HSD and MCT? What do you think is the cause for different young ages of BT, Bakrita thrust and main central thrust?
Okay, the Kalopani, for up to now, we found the Kalopani shear zone only in the Kaligandaki Valley. In the other section, we were not able to find a similar shear zone. But probably there are two reasons, because the Kaligandaki Valley is a valley where we have few leucogranites. So usually, for example, the Manaslu massif is a huge intrusion of leucogranites, including the upper part of the GHS. So a shear zone could be not so easy to observe. And another reason is that in the upper part of the Great Himalayan sequence, there is a huge ductile deformation due to the South Tibetan detachment. And a high temperature, low pressure metamorphism with cordierite, andaluzite. So the condition to preserve a solid state shear zone in the upper part is very difficult. Maybe it is much more difficult to detect the occurrence of this upper shear zone with respect to the HHD, because it is in the lower part, not so affected by granites, by high temperature metamorphism, and by extensional deformation by the South Tibetan detachment.
Yes, thank you. So another question from Arik from Kenya. He's asking, or she's asking, is Himalaya a range of mountains, or is it a single mountain? And is Everest one of the peaks of the Himalayas? So more general question from African colleague.
I think the Himalayan range is not a single mountain, but of course there are several mountains, several belts. And of course Everest is one, and is the main peak of the Himalayas, the highest peak.
Okay. So again, following the question Dr. Boral is asking, so Professor, if I'm not wrong, then you link the MCT with the younger thrust, like Mansuari thrust. Do you mean that the late activation of main central thrust is 5 million years and then remain stable?
Okay, so I am not wrong than the mental thrust. I don't know. we can we can only have detection of the lower of the Mansuari thrust with white micas at 4 or 5 million years. We have found other shear zone below. I don't remember the local name, but there were no minerals suitable for detection. So I think. I believe, I hope that the deformation shifted further to the south, but we have no means to date the lower shearing. We can try to date maybe calcite or some small white micas, but it is much more difficult. But we will try in the future.
Yes, thank you. I think I don't see any questions, but I have some observation, because as being a science of earth, as being a student of geological science, I'm not so much deep into this metamorphic course and others, but when I heard or read your papers about this HSD, between these MCT and STDs, and so are there? I don't know. This question might be a silly one, but is there any relationship between the division made by Patrick Lappert about the Himalayan crystalline mineral domination from MCT to up to the STDs with this HSD, what you are mentioning here? And do you think there is only one HSD, or there might be another 2 or 3 HSD in the Himalayan sequence? Or what's your observation on that?
Okay, for what I know from the main Himalayan range, I can say that there is a ductile shear zone in the South Tibetan detachment and the upper brittle normal fault, cut by high angle normal fault. But for example, we had the data from one PhD students in China from the Yalazambo Dome, when we were able to date two different ductile shear zones at maybe 24 million years and 18 million years, and then a brittle fault. So probably there is a shifting of normal shearing also in the upper part, but it is difficult to go in the field because some of the most beautiful outcrops are in China, in southern Tibet, and it is very difficult to go in the field to take sample. But I think there is a similar shifting of a younger deformation towards the higher part, from ductile to brittle with different stuff, different shear zone, I think.
Yeah, there is one question in Facebook, but before that, I think this will be a last question. But before that, I have another observation. So, people are discussing about India-Asia collision. Some people argue that, it happens, collision happens at central and shifted to the east-west, or it got collided in the west and then counterclockwise rotation or somehow. So what's your observation on these collision between India-Asia and then link with the metamorphic origin of this Himalayan region?
So I am not sure to have understand well. Do you mean different ages of collision in between from western to eastern part?
No. Some people say that India-Asia collision happened at central portion of the Himalaya and then shifted east to west. Or some people say that it collided first in the west and then later shifted to the east. Something like that.
Yeah. I don't know exactly because I have no data to say something about this, because we are working on all their deformation. What I can see from the bow shape of the Himalayas, maybe deformation is much faster in the central part, because the metamorphic rocks are in a southern position with respect to the Nanche Barva or the other syntaxes. But I have no data to say something about these different opinions.
Yeah, because still it's a hanging discussion, and probably when I read the paper from Dr. Boral, that their group, his group, saying that stated that the collision took place at central and later shifted east to west, and some other people say that contrary. So the last question from for this talk from Bhupati Nupane in Facebook. So he's asking how metamorphism of rocks are affected by two major thrust, MCT and STDS.
Where is the question?
Yes. So question is how metamorphism of rocks of the higher Himalayan, greater Himalayan sequence are affected by two thrust MCT and then the STDS.
Maybe along the main central thrust, what I observed from the microstructure is that we have shear plane after Barrovian metamorphism, after kyanite, after staurolite. So metamorphism before shearing, and the same along the South Tibetan detachment, but probably some people explain use some shear heating that can increase the temperature, not so much, but up to 70, 100 degrees of temperature due to shear heating along the main central thrust. There are some calculation by Molnar in the 90s, if I don't remember bad. So a little bit contribution from the thrust to heat the rocks could exist, but it is a small contribution because you are dealing with rocks experience the 700, 800 degrees of temperature, and you can increase the temperature of the lower part of 70, 80, 100 degrees, also maybe the same from the South Tibetan detachment. So a small contribution, I think, by shear heating on thrust fault.
Yes, Thank you, Professor Carosi, and always Himalaya is complex and
yeah,
it's inaccessible. But these days, due to this good road construction, we can go at least by car in some region, and then we can climb up. That what I mentioned, in 60s when Moderator and Pierre and others, and then Laporte, and then Fuchs and Frank, and then our colleagues working in the Himalayas. So it's it started from expedition, and now it's getting easier and easier to reach the mountains, and hopefully, more research will come in future. And I also, encourage our, everybody will encourage our Nepalese geoscientists to work on this regards, or, the Himalayan geoscientists starting from Pakistan, India, Nepal, and Bhutan to work together to, to find the answers about this evolution of the Himalayas in different part of the Himalayan arc. And so, before I hand over to Suraj Gautam, and so do you want to say any final words, Professor Carosi?
Any final? Sorry,
final,
I have some difficult of connection sometimes, and I lose. Words.
Yeah. Before I hand over to Suraj Gautam, do you want to say any final words?
Okay, of course. Thank you to all of you for the attention, for the very interesting question. The Himalayan belt is one of the most well-studied chain of mountains in the world, but there are still hundreds or thousands questions still open, starting from the main center trust, defined 80 years ago, but still it is a controversial topic for the position, for the definition. So there is a lot of work to do. And for my experience, I started only by field geologists and structural geologists. My feeling is that we can link several disciplines together to gain a little better knowledge of the mountain belt. For example, metamorphism, geochronology, or erosion, the title zircon. So all the things must put together. It is not easy, absolutely, but it is the way to follow, because looking only at a single discipline on the single aspect is not so good to have good interpretation and good knowledge. So put together all different kind of data, discipline, and interpretation could help in a better understanding of the Himalayan belt, as well as a lot of field work. Field work is essential, because sometimes people like numerical models very much. They are fascinating, but we must not forget the field work, the field, the structure in the nature, what the nature says us. Okay.
Yes.
Thank you very much for your
Thank you, Professor Carosi. Before I hand over to Suraj Gautam, I would like to request Professor Kaviraj Paudel to say final words, because he's working with Professor Carosi for a long time. And so, Professor Paudel, can you just say final words a little bit?
Okay.
Hi, Kabi.
Okay. Namaste from Nepal. Yeah, very nice presentation. Thank you very much, Professor Dr. Rodolfo Carosi, for your presentation. Very nice interaction. So you have explained very nicely, and there are several questions about Himalaya. It is never ending. Yeah, and we are at the very primitive stage of the research. You have done a lot of works in Nepal, Himalaya. So I think you were born for Nepal and as a whole to Himalaya. Thank you very much for your research, and you choose Nepal, Himalaya for your research career. And still we have many questions to our young students. So I request you to provide your research papers to our students.
Yes, I'm happy to send you the paper, no problem at all. Yes. Send me the paper that you would like, I share them.
Okay, thank you very much. Thank you, Basanta, for your everything you explain and you bridge and you conduct this webinar, this research presentations very nicely. Thank you very much.
Thank you, Professor Paudel. Now I would like to say very few words, Professor Mary Hubbard.
Oh, you're putting me on the spot, but I'll say namaste. And thank you for that great presentation. It was fun to see all your recent work. Well, probably not all of it, but a lot of it put together in one place and compiled, and it tells a nice story. It seems totally consistent with all the things I observed, even though that was many years ago on the MCT in Eastern Nepal. So thank you very much. And I really, again, want to emphasize a thanks to the organizers of this webinar series. In a way, you know, none of us likes COVID, but there are a few things that have been really nice outcomes from the situation we've found ourselves in. And to be able to have a seminar like this, that for me, it's Sunday morning here, but to wake up and be able to see all my Nepali friends, and then someone like Rodo giving a nice presentation. So I thank the organizers for putting this together as well. And then the fact you're archiving these seems like that makes it really nice as well from a teaching point of view for any of us around the world to be able to draw on some of these resources, and students will enjoy these presentations. So yeah, thank you, Rodo, and thank you, organizers.
Welcome.
Thank you, Mary. So now I will hand over to Suraj Gautam. Please proceed.
Thank you so much, Dr. Basanta, for the, as always, excellent moderation. Well, we really had an interesting episode with a number of practical experiences, and it was really good to hear from Professor Kaviraj Paudel and Dr. Mary Hubbard for the wonderful remarks as well. And we'd like to thank Professor Dr. Rodolfo Carosi for the wonderful review on the architecture of metamorphic core of the Himalaya. And we also had a very interesting Q&A session with a number of good questions. We tried our best to address all of the questions from the Facebook live streaming also, and also from the Zoom chat box. In case you have any further queries, or in case you want to ask for some papers, you can please feel free to email us at info@inhrr.org. I would also like to convey my big thanks to all of our organizing team, speakers, session moderator, our distinguished guests and participants for participating in this session. The session was really informative and it was really interactive. We'll be sharing the recorded session on our YouTube channel, and the links will be forwarded to the registered email. We also have a scheduled webinar episode on Geo-Science for Sustainable Development this September 6, 2020. That is at 8 p.m. The regular time which we are having, and the topic is related to understanding of sediment provenance and diagenesis using stable isotopes in phosphates, which will be presented by Dr. Dev Prasad Jaisi, who is an associate professor at Department of Plant and Social Sciences, University of Delaware, USA. We'd also like to request our participants to please fill up the feedback form, where we'll also be we'll also be able to receive some of the future webinar topics. You can also suggest there. And we'd also like to mention that Institute of Himalayan Risk Reduction will be more than happy to collaborate and organize this kind of relevant webinars in the days to come. So with this, I would like to sign up from our session for today. Thank you once again. Namaste. Stay safe.
Namaste. Bye-bye. Namaste. Bye-bye. Thank you. Bye-bye. See you.
Thank you very much. Bye.
Thank you.